Welcome to this video on the secret identity of magnetism, where we explore how Einstein's relativity fundamentally reimagines a core force of nature. Classically, we learn a simple rule: moving charges create magnetic fields. This current in a wire deflects a compass and exerts a force on a nearby moving charge. But why is this true? Einstein proposed a startling alternative. What if the magnetic force is not a separate force at all? What if it's simply the electric force, or Coulomb's law, viewed from a different frame of reference? From our perspective, the wire is electrically neutral because the number of positive protons equals the number of negative electrons. If the wire is neutral, Coulomb's law predicts zero electric force. So where does the observed attractive force come from? Let's change our perspective and ride along with the moving electron. From this new frame, the charge count still seems balanced. For every stationary electron, there is a moving proton. The wire still appears neutral. What are we missing? The first clue comes from special relativity. Moving objects appear shorter. The length of an object shrinks in the direction of motion when viewed by a stationary observer. This is length contraction. In the electron's frame, the moving proton's spacing contracts, increasing their density. The stationary electron's spacing expands, decreasing their density. Relativity changes the density of charge. This relativistic charge imbalance creates a net positive charge on the wire, resulting in a measurable electric force on our stationary electron. The quote, magnetic force was simply an electric force in disguise. We now face a new puzzle. Why do parallel currents attract? Coulomb's law predicts powerful electric repulsion between the two parallel electrons. Yet, experiments show they separate slower than expected, as if a magnetic attraction is partially canceling the repulsion. The second clue is time dilation. Special relativity states that time passes slower for a moving object when viewed by a stationary observer. Any process, including the separation of particles, appears to happen in slow motion. In the electron's frame, the electrons separate at normal speed, as predicted by Coulomb's law. In our lab frame, we observe this separation unfolding more slowly due to time dilation. The slower separation isn't a new force, it's electric repulsion viewed through a distorting lens of time. We are left with two forces, but one reality. Electric and magnetic fields are not distinct. They are different faces of a single, more fundamental entity, the electromagnetic field. What you perceive depends entirely on your relative motion. This relativistic model beautifully explains magnetism from currents. However, it doesn't fully explain phenomena like the intrinsic magnetic field from an electron's quantum spin, which exists even when the electron is at rest. Charge is conserved, so if the neutral wire becomes positively charged in the electron's frame, where did the net positive charge come from? In summary, magnetism is the electric force viewed from a different inertial frame. Length contraction creates observable charge densities, and time dilation can make forces appear weaker by slowing down processes. The forces we experience every day are shaped by the very fabric of space-time. A simple change in perspective, guided by relativity, can transform one fundamental force into another.